The reactivity series is a way to rank metals based on how easily they lose electrons. Metals at the top of the series, like sodium and potassium, are highly reactive and will readily give up their electrons. Metals at the bottom, like gold and platinum, are less reactive and hold on to their electrons more tightly. Understanding the reactivity series is important for predicting how different metals will behave in chemical reactions. The vibrant colors and scientific instruments in the background image help visualize the dynamic nature of these chemical processes. Metals are unique elements found naturally on Earth, with distinctive physical and chemical properties that make them useful for various purposes. Metals play a crucial role in numerous industries, from construction and manufacturing to electronics and energy. Metals have been used by humans for centuries, shaping civilizations and advancements throughout history. This slide provides an overview of the key aspects of metals, including their elemental properties, industrial applications, and historical significance. Metals are made up of atoms that are arranged in a regular, repeating pattern called a crystal lattice. The atoms in metals are tightly packed together and have a strong attraction between them, known as metallic bonding. This tight packing and strong bonding gives metals their characteristic properties, like high strength, conductivity, and malleability. The crystal lattice structure and metallic bonding are what give metals their unique atomic-level structure and behavior. Understanding the atomic structure of metals is key to comprehending their physical and chemical properties. Metallic bonding is the type of chemical bonding that occurs in metals of valence electrons are released from the outer shells of metal atoms, forming a sea of delocalized electrons. This sea of electrons surrounds the positively charged metal ions. The strong electrostatic attraction between the positive ions and negative electrons is what creates the metallic bond. This metallic bond is what holds the metal atoms together and gives metals their characteristic properties. Metals have the unique ability to be hammered into thin sheets, malleability, and drawn into wires, ductility. This is due to the way metal atoms can slide past each other without breaking the metallic bonds. Most metals have a shiny, reflective surface, luster, because of the free electrons in the metallic lattice that can absorb and re-emit light. Metals are excellent conductors of heat and electricity, also due to the free movement of electrons within their structure. Metals are generally very dense, with a high mass per unit volume, because their atoms are closely packed together in the metallic lattice. The reactivity series is a list of metals arranged in order of their decreasing reactivity, with the most reactive at the top and the least reactive at the bottom. This is a useful tool for predicting the outcome of reactions between metals and other substances. The table shows the different metals and their relative reactivity, ranging from very high for potassium to very low for gold. Understanding this reactivity series helps explain phenomena like metals reacting with water, oxygen, and acids in different ways. The more reactive a metal is, the more vigorous its reactions will be, releasing hydrogen gas and forming metal oxides or salts. Displacement reactions, where a more reactive metal can displace a less reactive metal from its compound, are also based on this reactivity series. Alkali metals are the highly reactive elements in the first column of the periodic table. They are soft, silvery white metals with low melting points. These metals react violently with water, releasing hydrogen gas and forming alkaline solutions. Their reactivity increases as you move down the group. Alkali metals readily lose their single valence electron to form stable salts with nonmetals. Despite their reactivity, alkali metals are found in nature in mineral compounds and salts, not in their pure elemental form. Alkaline earth metals are the group 2 elements on the periodic table. They are reactive, but less so than the alkali metals. They share similar chemical and physical properties due to their electronic configurations. Common examples include beryllium, magnesium, calcium, strontium, barium, and radium. They readily react with water and oxygen, forming oxides and hydroxides. These reactions are often exothermic and vigorous. Transition metals are a group of elements in the periodic table's d block. They have partially filled d orbitals, which gives them unique properties. These include variable oxidation states and the ability to form colored compounds. Transition metals are generally hard, dense, and have high melting points. They are good conductors of heat and electricity, making them useful in alloys. Key examples include iron, copper, gold, silver, and nickel. Transition metals are vital to many industries like construction, electronics, and medicine. They are used in building materials, electrical wiring, medical implants, and catalysts. The noble gases are a group of colorless, odorless, and highly unreactive gases located in the far right column of the periodic table. They have a complete outer shell of electrons, making them very stable and unlikely to form chemical bonds with other elements. Despite their inertness, noble gases have many important applications, such as in lighting, lasers, and cryogenics, taking advantage of their unique properties. Examples of noble gases include helium, neon, argon, krypton, xenon, and the radioactive radon. These gases are fascinating due to their stability and the way they challenge our understanding of chemical reactivity. Halogens are a group of highly reactive nonmetals in the periodic table. They readily form salts by combining with metals. In nature, halogens exist as diatomic molecules, two atoms of the same element bonded together. Halogens have many important everyday uses, from disinfectants like chlorine to pharmaceuticals and other industrial applications. They play a vital role in our daily lives due to their unique chemical properties and reactivity. The periodic table is a powerful tool for understanding the reactivity of elements. Elements within the same group tend to have similar reactivity due to their shared number of valence electrons. Moving across a period from left to right, elements become less reactive as they gain more electrons and their valence electrons are more tightly held. Reactivity also exhibits diagonal trends, reflecting the complex interplay between atomic size, electronegativity, and ionization energy. Understanding these periodic trends is key to predicting and explaining the chemical behavior of elements. Electronegativity is a key factor affecting reactivity. Atoms with high electronegativity readily attract electrons and are more reactive. Ionization energy is another important factor. Atoms with lower ionization energy, meaning less energy is required to remove an electron, tend to be more reactive. Atomic radius also plays a role. Larger atomic radii generally correspond to lower reactivity, as the outer electrons are further from the nucleus. Finally, activation energy is critical. Reactions with lower activation energy barriers are more likely to occur, leading to higher reactivity. Understanding these four key factors, electronegativity, ionization energy, atomic radius, and activation energy, is crucial for predicting and explaining the reactivity of different atoms and molecules. Electronegativity is a measure of an atom's ability to attract electrons in a chemical bond. It increases across a period from left to right as the effective nuclear charge increases. Electronegativity decreases down a group as the distance between the nucleus and valence electrons increases. This trend is related to the changing ZeF, effective nuclear charge, and atomic radius. The periodic table is a useful visual tool to see these electronegativity trends. Electronegativity differences drive the formation of ionic and covalent bonds between atoms. Ionization energy is the minimum energy required to remove an electron from a gaseous atom in its ground state. It measures the strength of the attraction between the nucleus and the outermost electron. Ionization energy generally increases across a period due to the increasing effective nuclear charge. Ionization energy decreases down a group due to the decreasing atomic radius. Electronegativity is the ability of an atom to attract electrons in a covalent bond. Electronegativity also increases across a period and decreases down a group, for the same reasons as ionization energy. The trends in ionization energy and electronegativity are important for understanding chemical reactivity and bonding. Atomic radius is the distance between the nucleus of an atom and its outermost electron shell. Atomic radius generally increases as you go down a group in the periodic table. This is because as you go down a group, the number of electron shells increases, causing the atom to get larger. Conversely, atomic radius decreases as you go across a period in the periodic table. This is because as you go across a period, the number of protons in the nucleus increases, causing the atom to get smaller. Oxidation and reduction are fundamental chemical processes that involve the transfer of electrons between atoms or ions. Oxidation is the loss of electrons, which increases the oxidation number of a species. Reduction is the gain of electrons, which decreases the oxidation number of a species. Redox reactions involve both oxidation and reduction occurring simultaneously. These processes are essential in many chemical reactions and have important applications in areas like energy production, material science, and biology. Oxidation numbers are a way to track the movement of electrons in chemical reactions. They represent the hypothetical charge an atom would have if all its bonds were ionic. There are a set of rules to determine the oxidation number of an atom in a molecule or ion. These rules help us predict the behavior of elements in chemical reactions. Oxidation numbers are critical for balancing chemical equations, understanding redox reactions, and predicting the stability of compounds. They provide a useful tool for chemists to analyze and understand chemical processes. Corrosion is a serious problem that affects many materials, especially metals, due to chemical reactions with their environment. There are several different types of corrosion, including uniform, pitting, galvanic, and crevice corrosion, each with its own characteristics. Factors like moisture, oxygen, temperature, and the presence of electrolytes can accelerate the corrosion process. Fortunately, there are ways to prevent corrosion, such as using protective coatings, alloying metals, and cathodic protection. Understanding the causes and types of corrosion is crucial for developing effective prevention and mitigation strategies. Passivation is the process where a metal reacts with its environment to form a thin, stable oxide layer on its surface. This oxide layer acts as a protective barrier, preventing further reactions and protecting the underlying metal from corrosion. Aluminum and stainless steel are two common examples of passivated metals that exhibit enhanced resistance to corrosion. Passivation is widely used in various industries to protect metals from degradation and extend their lifespan. The galvanic series is a tool that arranges metals and alloys based on their tendency to corrode in a specific environment. It's a crucial tool for preventing corrosion in many applications, as it helps predict corrosion rates and the direction of electron flow. The galvanic series allows us to select compatible metals for different applications, ensuring reduced corrosion. The image on the slide shows a diagram of the galvanic series, with a color gradient indicating the relative nobility of the metals and alloys. Understanding the galvanic series is essential for designing corrosion-resistant systems and making informed material choices. Cathodic protection is a technique used to prevent corrosion of metal surfaces by making them the cathode of an electrochemical cell. There are two main types of cathodic protection: sacrificial anodes and impressed current. Sacrificial anodes use more reactive metals like zinc that corrode instead of the protected metal. Impressed current systems use an external power source to provide electrons to the metal, preventing corrosion. Cathodic protection is widely used to protect pipelines, ships, and underground storage tanks from environmental corrosion. The key benefit is that it provides long-lasting, low-maintenance corrosion prevention for critical metal infrastructure. Metallurgy is the scientific study of metals, involving their extraction, refining, and processing. The process begins with extracting metals from their naturally occurring ores. Once extracted, the metals undergo purification and refining to remove impurities. The purified metals are then shaped and processed into useful forms like sheets, rods, and wires. Metallurgy is a crucial field that enables the production and use of a wide range of metal-based products and technologies. The extraction of metals is a multi-step process that begins with mining the desired metal-containing ore from the earth. The ore is then crushed and ground into a fine powder to increase its surface area, preparing it for the next steps. Impurities are removed from the concentrated ore using techniques like froth flotation, leaving behind a purer metal compound. The concentrated ore is then smelted in a furnace with reducing agents to extract the pure metal in its elemental form. Finally, the extracted metal undergoes a refining process to remove any remaining impurities, resulting in a high-quality final product. Metals often need further processing after extraction to remove impurities and achieve desired properties. Common purification methods include electrolysis, zone refining, and refining. Electrolysis uses electric current to separate pure metal from impurities. Zone refining gradually moves impurities to one end of a metal bar. Refining uses chemical reactions to separate impurities from the metal. Electrolysis is particularly useful for purifying metals like aluminum and copper. Zone refining is often used for high-purity metals like silicon and germanium. Refining techniques vary depending on the metal and its impurities. Metals are incredibly versatile materials with a wide range of applications. In construction, metals like steel provide the strength and durability needed for buildings, bridges, and other structures. Aluminum is also popular for its lightweight yet strong properties, used in aircraft, cars, and more. Metals are excellent conductors of electricity, making them essential for electrical applications. Copper is widely used in wiring, circuits, and electrical components due to its high conductivity. Gold is prized in electronics for its conductivity and resistance to corrosion. These are just a few examples of how metals are leveraged across different industries thanks to their unique physical and chemical properties. The mining and processing of metals can have significant environmental impacts that we need to consider carefully. Pollutants like heavy metals, dust, and chemicals can be released into the environment, contaminating air, water, and soil. Mining depletes finite natural resources, leading to resource depletion over time. Mining operations can disrupt and destroy natural habitats, harming biodiversity and ecological balance. The production and processing of metals also contributes to greenhouse gas emissions, exacerbating climate change. We need to find ways to mitigate these environmental impacts as much as possible through sustainable practices and technologies. Recycling metals is important because it conserves natural resources and reduces energy consumption compared to extracting new metals. Recycling also helps minimize pollution and greenhouse gas emissions. The recycling process varies depending on the type of metal. Aluminum cans are often recycled by melting and recasting. Steel recycling involves sorting, shredding, and melting. Recycling processes can be complex and require specialized facilities to handle the different metal types properly. The key benefits of metal recycling are conserving resources, reducing energy use, and minimizing environmental impact. Safety is paramount when working in a lab or handling hazardous materials. Always wear safety goggles to protect your eyes from chemicals or hot materials. Wear appropriate protective gloves to shield your hands from corrosive substances or sharp objects. A lab coat provides a crucial barrier against spills and splashes, keeping your clothing safe. Familiarize yourself with the location of fire extinguishers and emergency exits in case of fire. Following these safety precautions will help ensure your well-being and the integrity of your work. Metals are essential to our modern world. They are used in countless applications, from buildings and infrastructure to electronics and transportation. Throughout this presentation, we've explored the fundamental properties of metals, including their chemical reactivity, the nature of metallic bonding, and the processes used to extract them from ores. This conclusion slide aims to reinforce the importance of these remarkable materials and the insights we've gained about them. The warm, hopeful image of someone holding a metal ingot symbolizes the progress and possibility enabled by metals. They are the building blocks of our technological civilization. As we've seen, a deep understanding of the science of metals is crucial as we continue to develop new applications and innovations that improve our quality of life.